do the usual share screen. Put the presentation on presentation. Hopefully you could all see. That's nice.
Perfect. Very good.
There's always the bits in the way from Zoom on my screen. So today I'm going to talk on, as you said, what we've been doing, trying to work towards a nanoparticle certified reference material. I'm going to go through various different areas. That button there. But first of all, I'd like to acknowledge and thank all the co-workers on the project here, Nathaniel Clark and Richard Handy and Jack Baker here in Plymouth, and then Adam Laycock and Rachel Smith at the UK Health Security Agency. Invaluable work we've been doing together. So briefly, I'm going to give a sort of overview of single nanoparticle ICP-MS, how it works, what it does, what some of the problems are to it. And then a brief sort of description of what the steps are needed for method validation, followed by certified reference materials, what they are doing. So I'm going through some of the bits, maybe for some people who aren't necessarily familiar with all these bits, and then get into the real work we've been doing on the search for nanoparticles in existing CRMs, and then looking at whether we can use fish tissues which have been perfused with silver nanoparticle solutions as a substitute for a CRM. Then there's lots of questions that have arisen from this work, and then some future ideas, and then finally summarize where we've been to. So single nanoparticle ICP-MS, for those not familiar with it, is now sort of becoming probably the preeminent technique for the determination of nanoparticles in various different matrices, i.e. in waters, natural or artificial, and then tissues or solids where they've been undergo some form of extraction procedure. I have the fortune to review the literature annually on nanoparticles using atomic spectrometry, and there's about 50 to 100 papers published each year using single nanoparticle ICP-MS for nanoparticle determinations. And basically, with my we have a suspension sample here going through, peristatically pumped up to the spray chamber. I'm going to briefly pause there because the peristaltic pump tubing is one of the weak links in the sample introduction system, in that it needs to be in good condition and ideally brand new, but just sort of worn in so that your flow rate stays stable through the day. If it's using old pump tubing, nanoparticles stick to it and then get released at various points, sort of causing problems in the analysis. So we have material going in here, and we need to know one of the prerequisites. We need to know the flow rate of the material, of the suspension going into the instrument there. Then it goes through the spray chamber, which various proportions go to waste and some go forward to the plasma, only the very fine droplets containing the nanoparticles. So that would be termed the transport efficiency, how much of what goes in actually gets to the plasma. And that's another key measurement area we need to make before processing with realized data. So the droplets travel through down into the plasma, desolvated, and the nanoparticles are broken down into atoms. Some are ionized, and then you get through to the mass analyzer, where you end up with an idealized form of a spectrum with signal intensity against time. And the larger this signal here, the greater the size of the nanoparticle. In theory, it works on a basis of probability that one nanoparticle will fit your individual measurement period of somewhere between sort of 0.1 and 5 millisecond duration. The timing there depends on the hardware of the instrument, what it's capable of, not least how quickly it can actually transfer and record the data. This then gets processed by using the metrics that we've already measured for the sample flow rate and the transport efficiency. in there, we can end up with that enables us to calculate particle size distribution, particle number concentration, i.e. how many there are in your sample originally, and then the mass, so the mass of your nanoparticles in solution, with a big assumption, of course, that particles are spherical and you need to know the density of the particle, which for single element particles is straightforward, but if you have multi-element particles, that can get more complex because they need again to be well characterized. As I said, it's becoming a routine common method for doing things. So whilst we have a routine method, what we really need to move on to is to how reliable and how well it's operating. Just put a couple of pictures in there to zoom in. So this is a real data from 20 nanometer particles analyzed at 5 picogram per mil suspension concentration, and you can see the real scan data in there. So each of those signals represents ion cloud coming from each individual nanoparticle, the intensity varying with size, and then you have the sort of baseline signal down the bottom, which is from dissolved silver in this case in solution, which as it was a blank, there's very little. One of the problems that could arise is that if you have a natural tissue sample, which has what I'm going to use the term for throughout, ionic silver in there, i.e. silver dissolved or somehow in the tissues in there, that gives you an increased baseline, which could easily run up at much higher levels, which then your nanoparticle signals sit on top of that, and that increased baseline reduces your size detection limit. And you can see on even at this picture here, there's a detection limit, a size distribution which tails off nicely at the higher level, but it's cut off down at the lower size on there because the baseline signal is still too high to be able to measure distinguish nanoparticle signals from the ionic signal in there. And with this one is a suspension. We managed to, as you'd hope, you can measure the nanoparticle diameter and the concentration to a reasonable degree of accuracy compared with the manufacturer's stated dimensions and the concentration from dilution. So moving on to brief things on method validation, it's effectively say, are we measuring what we really want to measure? And we need a number of different steps to be able to say that. So selectivity, specificity, are we measuring nanoparticles themselves, or is there an artifact in the way of measuring things? Various different other parameters on the left-hand side that we need to evaluate through to it. One of the key ones is where this is leading to is sort of a biased trueness evaluation. You really need something, a material with known values for the parameter under test, i.e. the nanoparticle size in this case, or the number concentration or the mass concentration in a thing. It also requires an uncertainty statement to have it, so you can compare your method with that and give some metrological traceability to your results. In other words, what we're looking for is there is a reference, or ideally a certified reference material. So currently there aren't any available for tissues. There's only pure suspensions of nanoparticles available. So we can't validate really the extraction procedure very well. But what about spiking experiments is what people often use in that. Excuse me a moment. This is, if you're spiking on nanoparticles onto a sample, your aim is to get back the amount recovered, but it doesn't tell you anything about the original amount of analyte in there present in the first place. It just tells you that you can get back or not what you've added on top of the original amount. You can then use that, of course, in conjunction with a mass balance approach where you compare the sum of the nanoparticles and the sort of, again, use that phrase, ionic fraction content to the total done by a total digestion method. And then there's the third area, which is also of concern, is artifact formation. You need to demonstrate your extraction reagents do not promote particle formation. So one of the commonly used extraction solutions from to extract nanoparticles from biological tissues is tetramethyl ammonium hydroxide, TMAH for short, which in solution typically has a pH greater than 10. And at that pH, a lot of metals, silver included, if you look at the Pourbet diagrams, in an oxidizing environment will tend to form solid precipitates of oxyhydroxides or similar. So if there's ionic silver present, you can end up converting it into particulate format, which is an artifact and appears in your blank solutions. So that needs to be checked as part of the method validation as well, that that's not happening. Certified reference materials, we move on. So a whole brief suite of what they are, and their whole things need to be characterized and stable. And as I said earlier on, CRMs, they're not available for tissues, so we need some. They're costly to produce. Kilogram quantities are needed. So if you can imagine trying to produce a nanoparticle fish tissue, for example, that would be prohibitively expensive. I'd hate to think of the cost for involving in that, but I suspect it would run into hundreds of thousands of pounds, dollars, euros, zlotys, whatever currency you want to think of. So there's another concept that can be thought of as a representative test material, which is, there are certified reference materials for various fish tissues out there already, but you could put about and see if there are any nanoparticles in there as a material. So these samples have already been prepared and produced, so we can just adapt them for a different purpose, which may, as they're already then lead on to them being able to be certified by the producers for those extra analytes. So what we did in this, and this was master student project work that we did, so thanks to Jack for sort of 3 months of work going through here. We looked at 3 different fish tissue CRMs, a dogfish liver, a dogfish muscle, and a lobster hepatopancreas, which are available, and they're certified for a range of metallic elements. We had a brief procedure described there to extract the nanoparticles, and we're attempting then to see what we could find in terms of nanoparticles. Are there any in there? Are there any present? If so, how repeatable is the procedure? Calcium chloride solution is used in there to inhibit the formation of nanoparticles from onyx silver present in the tissues in there. And again, we see a same thing there as showed you earlier on for the standard for nanoparticle suspension. This is an extract from a dogfish liver tissue using TMAH as the extraction procedure. And you can see on the left-hand side, there are some particle signals. That's good. You can see what I talked about, the elevated baseline from the endogenous ionic silver in the material. So that has raised the detection limit slightly. And you can see we've got a particle size distribution for it. Came out overall at sort of 18 nanometers for it. That's one representative. So Jack did an awful lot of different replications on those 3 materials to see whether everything is suitable and whether everything comes through as, are they homogeneous materials. 3 months work comes down into one table of data, which particle size, so the sort of column towards the right is what I'd like to focus on most there. Yes, we were able to detect nanoparticles in there, but the uncertainties, which are just one standard deviation, are large, and that's from a large number of replicates there. So what we're thinking is perhaps these materials aren't very homogeneous. They're homogeneous with respect to the ionic sort of distributed material. Maybe the nanoparticles are less well distributed within the material. That may be down to the sample size we took, which was 50 milligrams or so, or 25 milligrams, which was designed to represent the amount you might use for a natural fish tissue from an ecotoxicology study, where you're only ending up with small samples of that. So you possibly need to go back and repeat this work again using much larger sample sizes. But at those sort of levels, it's not really suitable. We can detect something, but it's not really suitable. I should put a word on the sample size. Actually, the amount you need to take depends on the particle size distribution, the material you're using. So the coarser the material, the larger the particle size you need, sample size you need to take to be able to get a representative sample. So this is the first part. A bit disappointed that the results weren't as precise as we'd hoped on this one. So what did we do next? Well, we thought, can we create our own fish tissue reference material? You know, what are the ways of doing that? Well, as I said earlier, we could create a fish feed spiked with nanoparticles. We do for the ecotoxicology. Grow fish on this feed, harvest fish, process, analyze. And I alluded to 10 to the X is my thing of how many dollars, pounds, euros it would take. It really probably wouldn't be commercially viable. There's a pressing need for it. I suspect that it just wouldn't be cost effective to do it this approach. Someone from BAM or IRMM, for example, might think differently. It'd be interesting to hear from them. So what then did we try? Well, there's an approach you can take where a fish, its heart will still carry on beating instantly after dispatch for a short while. So you can replace the blood in the system by perfusing a solution, saline-based solution, into the heart, and you fill that, and it sort of effectively fills the vascular system, or the vascular system of the fish. So we tried that on 5 different fish were perfused with nanoparticles, 5 controls, and each fish in total was about 200 grams. You can see where I'm talking about the amounts you'd need, number of fish you'd need to grow, because that liberated 1.5 grams of gill and 2.5 grams of liver from five fish each time. So we're talking 0.5 gram per fish. So it's an awful lot, a couple of thousand fish per kilo of material. We then went through on the conscious of the time I'm going through here, went through and used the same extraction procedure as before on there, with 2 sample sizes evaluated. And again, we did multiple replicates of each one and doing that. We did 2 sample sizes. And I say it was successful. We have the blanks at the top of the picture here where there's still some nanoparticle signals coming through. Could be from the spiked in ionic silver forming nanoparticles. They just as likely to be individual nanoparticles dislodging from the sample introduction system somewhere. The control liver extracts had some nanoparticles shown in there, but very few. And then right at the bottom, you've got the liver extracts of the nanoparticle ones, showing a good deal of nanoparticles in there, as you'd expect, because we'd added them to it. We also did the same with the gill samples, which leads us on to particle size distributions for the 2 different sample types. These were nominally 60 nanometer nanoparticles. We've measured them repeatedly and they come out about 56. You can see there instantly there's a very broad tailing on distribution. That's almost certainly due to the fact that you need to suspend them in a saline solution to be able to perfuse them through and transport it through without disrupting the tissue structure of the fish. So that's probably what's caused this aggregation, agglomeration of particles and doing out there. So, okay, there's a bit of work to do on there, but broadly successful in that this particle sizes both coming out at similar size in there, larger than we actually put in. But if they would remain at that size, then that's not a problem, because we need to characterize what the actual size in the material, not what we put in. So one table again to put the material in. I just concentrate on the particle size at the moment. RSD's over the 3 different replicates coming out at 3 or about 3% for both the gill and the livers, which that is fairly good from what we thought from overall 9 replicate measurements. Particle number concentration varies. When Nathaniel perfused the fish, you could instantly see the gills went very, very grey instantly. So there looked to be a very homogeneous distribution for it. But in the liver tissue, the coloration was patchy. So we think we've probably got a heterogeneous liver tissue sample, because we're dealing with such a small amount. Actually turning that into a finely divided material has proved a bit of a challenge. But overall, it's showing progress. The uncertainty on those 1 standard deviation, and they would rise significantly once a full uncertainty estimate was made of it, taking into account all the parameters of the method involved, which was also proved quite challenging, but one of my fortes. So are the results acceptable? That's a question we're just posing. That's something to think of. The other question is this a sensible idea at all? So what we're effectively doing is a spiked fish tissue, if you like, but spiked internally rather than added onto the outside. My time's probably coming up. So here are the questions, Andrea. Are they studies too large? How we compare with the literature? We need to reevaluate that and jump to the bottom one. Shameless plug of where we live in ever sunny Plymouth. And there's one of our research vessels in there. And to misquote from the film Jaws, if you may remember it, instead of needing a bigger boat, we need a bigger fish to be able to work with more material, to be able to understand this process better and whether we can produce enough material and it's sufficient homogeneity to be able to measure things correctly. So my final slide, a brief summary of it. We've had a look at the existing tissues, and I think there's positive there, but I need to go back and look at the data. I think there were possibly issues with ionic silver forming nanoparticles with that work. Uncertainty is possibly too large in there, so we need to work that down to it. We've made some progress, but there's a way to go, not least, as I said, thinking about whether this is a sensible approach. So anyone else's input into that. Thank you very much for listening, and thanks again to my co-workers on this project.
Great, Rob, and thanks a lot for the presentation. And we are a little bit with the time. You are exactly finishing with the time of discussion.
Cool.
And you were really pausing or giving or presenting quite a few of those questions. And I think what I gathered, it was the quantification and the sizing that were the 2 points you were addressing. And the sizing, from what I saw, even though coming from our aerosol science, the size distribution somehow look a little bit more nice mostly. So here you see the tailing and the peak is there. But was the size you were giving indicating the 7 to 72 nanometers around that one? of the material? Was that the median diameter, or was that the average diameter? What type of diameter was it? So that was unclear to me. And then certainly the question arises, is this standard deviation you were assuming based on a Gaussian curve, or what was the root, yeah, the uncertainty level you were indicating there based on?
Okay, so the first question, I need to check back on the calculations for whether it's the median or the average on that. I'll have a look and pop the answer in the chat later on. The second question, so we did 3 replicates of each tissue type, and we analyzed them 3 times each. Okay, the same extraction. The value there is simply the mean of the mean of each the 3, so it's the minimal one. So if I was to use the concept of the uncertainty within and the uncertainty between, it's just the uncertainty between the 3 samples. So if I took in the within sample replication from the 3 measurements on the same one, that's where the uncertainty would instantly rise straight away. That last bit was hot off the press from Friday's analysis. It's yet to really fully dive into get the uncertainties worked out. It was more a case of presenting, we've got some ideas and they may work, but are we being sensible or not, I think is the key statement.
Very good. And yes, please indicate that in the chat later on for this information. The second part on the quantification, it was interesting. I think it was the liver, where the number concentration you determined was very similar between the sample of 25 and 50 milligrams per milliliter. The quantification, would you also say that the quantification will be within the tissue will be a larger issue than the size distribution? That's what I gathered from your presentation, but maybe my impression is wrong.
It seems to be varied from the liver. So the gill was particle number concentration, for the RSD values were low, but there was a big variation, a big difference between them, which is odd. Without looking further into the data again, what we'd like to do is have more samples to try. We're limited on the amount of material we've got. It could be that we're again running into homogeneity issues with the overall material. We haven't been able to evaluate that completely and take more. One of the ideas with this material that we collected, we then pass on to colleagues at, I was going to say Public Health England, but they've changed their name, UK Health Security, and it was all safe, so they can then replicate and see their measurements. So we're a little comparison between, possibly with another laboratory or 2 as well. So we're trying to sort of not use the material, but we desperately need to, which is where I came back to the bigger fish needed to take this forward.
Good. I think it was a very good indication on the task, what we are really aiming for to work on the detection here in the tissue. And so we are really looking forward to how that will continue. Richard, just briefly, because of the time, I think you certainly have something very valuable to say. So Richard.
Just a very quick comment. I think with the tissues, the complexity of the vasculature in the organ is a key factor. With the gill tissue, the vessels are really big and you get the material deep into the tissue very quickly. With the liver, the sinus system in the fish is a bit more complex than that in the mammal. So that's probably the cause of the heterogeneity. But I think we can get around that with some other perfusion methods. So and maybe do that on a bigger animal, even something the size of a pig.
Very good, Richard. And I think it's very important to keep this information in mind when we use those for the testing and evaluating of effects in ecosystems and ecotoxicology. So thanks, Rob, and thanks to all your contributors for this excellent presentation. And I would then very happily go straight forward, after saying Rob goodbye now, to Keld, who is going to present the process being made in solubility and dissolution rate development. And I already see him looking around and starting his presentation. He is from NRCWE, and Keld, just go ahead, and I'm looking forward to your presentation.
Thank you very much, Thomas. I hope you can hear me well.
Perfect.
Good. Yes, so today I'm going to talk about the methodology that we have been developing here at the National Research Center for the Work Environment in Denmark, Copenhagen, Denmark. Basically looking into some ideas on how to make dissolution testing and solubility testing in a more biologically relevant approach, or following a more biologically relevant approach, considering the control of the test. And my co-author Yahya Kimbush has been the poor guy who's had to implement all the things in the lab, and working really hard to make it all happen. So first of all, I would like to just remind you on why we do this. So basically, the data on solubility and dissolution rate is required when it considers, or solubility is required for regulatory registration of chemicals, materials as well. But recently there's been a increasing focus on understanding the dissolution rate and solubility to understand persistence of fate of materials in the environment, but also in biological compartments. And a couple of years ago, it started seriously to also be embedded in regulatory requirements. So it is part of the requirements in REITs, and also in Canada and US and Asia. It's an information requirement that is coming up. Our problem is that we don't really have a methodology to determine the solubility, the dissolution rate of materials when it comes to an OECD method. And also currently there is a request to look into the biologically relevant compartments, and there was no documentation previously for that testing. So this is an example on excuse me, what is in the ECHA documents. Here we have solubility under the behavior, so where materials go and how they behave, and solubility actually in the guideline means both solubility and dissolution rate. What is written in the text is, of course, that there's not really any method available, but they would like information on water solubility and dissolution rates in biological media. And when it comes to biological media, it's very loosely described as the media of relevance. So we have to look into the pathways of the particles. And here we have mostly considered the gastrointestinal, the inhalation. So, and here we consider then the lung lining fluids and phagolysosomal fluids. So we launched a project at OECD, and we have had great support from, among others, Gov4Nano and NanoHarmony to support the developments of methodologies. In the two projects, we have looked into the atmosphere temperature and pH control stirred batch reactor system, where we consider this to be able to simulate initial to long-term solubility, as well as water and biodissolution. And you can, of course, put any liquid basically into the reactor. Here we have intended it for water, Campbell solution for the lung lining, and phagolysosomal fluids for the lysosomes and low pH 4.5. We also looked into a continuous flow system. Here the methodology is led by BASF in Germany. Here it's a system that simulates pulmonary uptake, and here you can mimic test hours to years of biodissolution. For the OECD work, it's considering the Campbell solution and phagolysosomal fluids. We also looked into the sequential gastrointestinal dissolution setup. Here, BFR in Germany is leading this approach. And the setup is looking into the dissolution through the gastrointestinal tract, so basically passing through saliva, stomach, and intestine, and the changes in pH from 6.4 to pH 2 in the stomach, and then going to the intestine with the pH 7.5. And we also looked into whether we could get some methodologies that were based on the existing test guideline or test guidance in OECD, so the GD 105, which was found inadequate for testing dissolution and solubility for biologically relevant media, and some modifications have been made. And here in October, we had a commitment from Yvonne and Grace to actually contribute with that methodology into our work. So here we again can have a link to existing OECD test guidelines and a methodology to simulate the long-term dynamic, water, and biodissolution. Here, the ambition is to look into both water and gamble solution and phagolysosomal fluid, and here we, of course, comply with the GD 105. And all of that goes into an interlaboratory comparison testing that is actually starting up now here in December. So you can still register for that if you are interested. So I'll be talking more about the atmospheric temperature pH control stirred batch reactor, or in short, the ATEMP SPR. Just a little information or description of the methodology. It's basically built up around the bidirectional titrator setup. We have made two sets coupled bidirectionally, so we have 4 reactors in total. So we can make a triplicate test and a reference in one go. And then the media is stirred by rods or magnetic stir, and then we have sensitive pH electrodes in each of the reactors, and you see the layout here with a pH electrode. We also added redox electrode because we can in fact also look into reactivity with the redox potential. We have the stirrer, and then we have on top of that atmospheric control. We use 5% atmosphere to be closer to the conditions inside of our organism. And then we have a entry for sampling. The liquid is, of course, thermostated through a water bath, and then we have flow controllers for the atmosphere, and then we use glasswares for humidifying the test atmosphere. We keep it in darkness with aerofoils and needle and syringes for sampling, and then we filter the samples after sampling immediately with 3 kilodalton centrifuge vials. In the work we do in the OECD, it's accepted to be in 3 to 5 kilodalton centrifuge vials. To get it all started, we use a batch dispersion procedure using a probe sonicator and follow here a what is called the nanogenotox dispersion protocol. And the whole setup has been tested and validated and published in the paper by Elsa Holmfred et al. Early this year. So what we get is a dissolution profile, and our standard setup is a 24-hour experiment, or was for the validation part. And then we sample at immediately after starting, 1 hour, 2 hour, 4 hours, and 24 hours after the experiment has been initiated. So after chemical analysis, using ICP, for example, or ICP-OES, we can establish a dissolution curve where you can determine basically the rate at different time points if you model this dissolution curve. So basically the data treatment is that you evaluate what type of dissolution curve you have, whether you have a 0 order or higher mixed order relationship between the time and concentration. And then we make a statistical regression curve, either linear or nonlinear, to determine the time point dissolution rate, so we can use that to calculate the initial or intermediate or last dissolution rate in the batch reactor setup. But we can also use this setup to understand something about the solubility limits. So when we go horizontal, no slope, then we, in principle, have the solubility limit in the batch reactor setup. So here about 7.3 milligrams per liter for a zinc oxide. So the good question is, because this is deviating from the way that the solubility testing is normally done, it's done consecutively, and then you take samples out and measure the concentration, of course, and then you are not allowed to have more than 50% variability between your samples from day to day, and you should have no trend in your analysis. So that means that basically you have a minimum requirement of 3 days or more for doing the testing. So one question we have is whether we can use the statistical approach to for the regression curve to calculate the solubility limit in a reliable manner, and this of course requires some analysis. So here we just see an example of basically the validation data we have on the dissolution rates in Gamble solution and phagolysosomal fluids. We looked into a range of materials, aluminum oxide, titanium dioxide. We tested the OECD industrial relevant materials here, NM104 titanium dioxide with aluminum coating, 3 different zinc oxides, 2 nanos and 1 non-nano, a silica material, serum oxide, and bentonite, which is a clay material, where we were able to determine dissolution for silicium, and we'll get a little bit back to that. What is maybe interesting here, I mean, we did 3 repeats of triplicates in Gamble solution, and then we did 1 triplicate test in the phagolysosomal fluid in this analysis. And what you see over here is the uncertainty level, percent uncertainty levels of the initial dissolution rate. So basically the dissolution rate at the very beginning of the experiments. And that's probably also the hardest one to determine, so the one associated with the largest uncertainty. But here we are with a median around a little bit above 10% in the Gamble solution, and around 4 for the median value in phagolysosomal fluids. And of course, we can have some deviations, especially when the solubility or dissolution rates are very slow, or we have very fast dissolution rates where greater uncertainty exists at the beginning. So the interesting thing now is to look into the solubility limits, and here we see some examples in low calcium Gamble solutions and phagolysosomal fluids and pure water. Here we have the nanopure water. Here we have the Gamble solution, and here we have the phagolysosomal fluids. You see a relatively low solubility apparently in the water, and slightly higher in the Gamble solutions, and even higher in the phagolysosomal fluid. And what you see over here is then the estimated solubility limit, what we find here with the statistical regression curve. And clearly there's a little bit of an issue here with the phagolysosomal fluid. We are not at the end, and the model indicates we do have some uncertainty also due to some missing values. So at least we have a solubility limit that looks like it's around 3.5, but we would need to look further into that. Here's another example. This is silica, the NM200 sample, and we see that in both water and Gamble solution, we do not really reach a plateau. We still have quite effective dissolution in both of these media, and considerably higher in the Gamble solution than in the nanopure water. And we see lower dissolution and solubility in the phagolysosomal fluids. So here we cannot determine the solubility limit because the solubility limit is way above the test concentrations and the duration of the experiment that we've done. For the phagolysosomal fluids, it seems like we can estimate something like 0.5 milligrams per liter in this experiment. Another example here is zinc oxide with water. Water, Gamble solution, and phagolysosomal fluids. And here again, we see different types of solubility curves and or dissolution curves, and we see modeled solubility limits, and the values are shown down here. And we, in our test, we use approximately 100 milligrams per liter in our test, so we can see that we are close to the solubility limit in our, close to the amount of material we have in the test. So basically, almost all is dissolved in this setup. So it also illustrates the huge difference there can be in the different compartments in the body when we look into these materials. The last example is a very low soluble material. So this is serum oxide. We did not identify dissolution below detection limit in the, or actually not detected in water and Gamble solution, and some low solubility in the phagolysosomal acidic conditions, which we see over here. So if we look into all the results, we can see that we have quite some variability in solubility limits determined with this approach. For the aluminum in the titanium dioxide, we see some dissolution in the Gamble solution, phagolysosomal fluids, but we didn't see any titanium dissolve. So titanium dioxide does not appear to dissolve in our setup. Aluminum oxide, we saw partly dissolution. For zinc oxide, we saw high dissolution, especially in the phagolysosomal fluids. In the silicon material, we saw that the slopes were not were still increasing. We didn't see any plateau, so we could not determine the solubility limits here, and we have moderate dissolution in the phagolysosome. For the serum oxide, very low dissolution and solubility in the phagolysosomal fluids. And for barium sulfate, which I did not show, there's more or less even solubility over 24 hours in both the water and Gamble solution and phagolysosomal fluids. When we look into the bentonite, we saw some issues here that we did see dissolution if we calculate it according to silicium, but not according to aluminum. And in fact, it's dissolving incongruently, and it looks like this is basically due to impurities with silica material in the bentonite. So it's not so easy to calculate the dissolution and solubility of the bentonite due to these impurities. And it would also require quite some additional time to actually get some dissolution of the bentonite in our setup. So the question now is how well did we predict solubility for the 24-hour experiments? And here we chose to basically look into how long, ask the question how long short-term dissolution testing is required for a reliable statistical determination of solubility limit. For example, can we say that we need specific dissolution curve characteristics, and we also need to consider the OECD GD 105 requirements for a good determination of solubility. We have chosen to look into the tier 1 materials from the interlaboratory comparison that is planned to start now. So basically the gamma aluminum, the titanium dioxide with aluminum coating, and the zinc oxide NM111 for this test. What we see here is a comparison between the 24-hour experiment and the 3-day experiments, and we see that for gamma aluminum oxide in the nanopure water, in Gamble solution, it's pretty much comparable what happens in these two media, so the solubilities are relatively close. When we looked into the phagolysosomal fluids, I mentioned before that this data set was not optimum. We seem to have some scatter, and indeed, when we did our second experiment, we did find a somewhat lower solubility limit for that experiment, and I think it's quite reliable as we see a very constant concentration over the 3 days in the setup. So this should be a reliable data set. So we see that the 3-day experiment improved the 24-hour test, and we are quite certain about the results here. If we jump to the aluminum oxide coated titanium dioxide, again, we didn't see any dissolution of the titanium dioxide, but we did see some dissolution of the aluminum, and we also saw an increase in the amount of dissolved aluminum when we increased the experiment or the duration for the 3 days. So in fact, even though the results looked quite okay, in the 24-hour experiment and the statistical prediction, we almost doubled the amount of material dissolved in the 3-day experiment. Unfortunately, we have a little bit of an issue with that experiment, so that should be repeated, but it looks like the actual solubility and dissolution happening over 3 days is higher than what we would expect from the 24-hour experiment. And now we go to the zinc oxide. For the Gamble solution, we see quite comparable results over the 2 experiments. We also see the plateau for the 3-day experiment. So here the results are good. They're slightly higher values. And when we look into the dissolution in nanopure water, we also see relatively comparable values, a little bit higher in the water, and we have a little bit of a strange behavior. It seems like the concentrations may be still increasing. So here we would need to do additional testing to confirm that we are okay. Last year in phagolysosomal fluids, we saw before that the dissolution in the 24-hour experiment almost reached the limit, and we see again also with the 3-day experiment that we are pretty much at the limit with a very weak increase also over time. And here's also probably we need to reanalyze and do the test here. So the results are quite new, but it seems like we are reaching the plateau at this point in time. So if we look now into the overall results, we have several experiments where we do see good comparability between the 24-hour and 72-hour experiments. There are some deviations, for example, here for the aluminum oxide in nanopure water, we were able to see aluminum dissolve after 3 days in water, which we could not see in the 24-hour experiment. So this is due to very slow dissolution of the aluminum oxide apparently in the water setup. In the Gamble solution, we saw an increase after 72 hours. So here we would also need to add on the experiment to understand more about the solubility limit and maybe the long-term dissolution rates of aluminum oxide in a battery reactor system. In the phagolysosomal fluids, we had improvements for the gamma aluminum oxide. We saw a slight increase in the 72-hour experiment for the aluminum oxide. We saw basically full dissolution of the NM111 in phagolysosomal fluids. So the results indicate that we should extend the duration of the experiments to get better data. So we should move from 24-hour to 3 days, where we can then probably both assess dissolution rates and also solubility limits in one experiment. Alternatively, we can do screening assays, for example, in 24-hour experiments, and evaluate from that point whether we would need extended durations for our testing. So trying to sum up, we see our system can be used to determine both the temporal dissolution rates and solubility limits of nanomaterials in both water. I should mention here the water was not pH controlled because nanopure water is extremely sensitive to any acid base, so it would go berserk if we started to titrate in that system. But long lining and phagolysosomal fluids can be kept very well at the pH conditions required. We can see we may assess solubility limits from short-term experiments, but probably our results are stronger if we use a 3-day approach. And of course, in some cases, the solubility limits may exceed the standard concentrations we look at, so additional testing may be required if we don't know the setup, or you have to use different concentrations in your batch reactors to address highly soluble materials. So we have a little bit of work to do still. So the final step is to rerun some single questionable or uncertain experiments, and then conduct the full statistical analysis for this work. And then I guess we are ready to go. So just a reminder, interlaboratory comparison deadline in a few days. We're happy to receive volunteers to join the experiment. You can contact me and Mark Gonzalez directly if you want to join. We have a two-tier approach where we would like everybody to test tier 1 and would hope for some contributions to tier 1, so we have a large number of materials in our interlaboratory comparison. And the methods are mentioned above and presented before, and yeah, we're happy to hear from you. So thanks a lot for your ears, and I'm happy to answer questions if you have any.
Yes, thanks a lot, Keld, for the concise summary of the work being done here on dissolution and dissolution rate, which is, I think, the most important part you were presenting here today as well. Yes, there are 2-3 questions for sure. One is coming from Ulla. Can the data be used for read across from one nanomaterial to another with the same chemical composition?
That depends a little bit on the material, actually. We have seen that zinc oxide is quite comparable across the materials, but silica, for example, the different types of synthetic amorphous silicas have quite different solubilities and dissolution rates. So one has to be a little bit careful. But I guess the general direction is probably relatively close, but you cannot say 100% certain.
Right. When you were presenting the data after 24 and 72 hours on dissolution, absolute concentration in the solution, you didn't indicate the uncertainty at that level, as far as I could see. So, how high is the uncertainty when you have this kind of comparison, where you were saying, okay, there is a big difference, you were indicating that, but it wasn't visible what the uncertainty level was?
No, I will add that I didn't do the statistical analysis for that at this point in time. I think that well, you can see some indication from these curves. These are the confidence intervals around the statistical regression curve. So we are normally, so yeah, it depends also on the amount and the quality of the data, but we are normally in, when you have these high values in plus minus 3 to 5, I would say, milligrams per liter in uncertainty, but, and that's in a triplicate test or a triple triplicate test. When you're in low soluble materials, you are of course considerably lower.
Right.
So it depends on the
relative uncertainties and absolute are certainly depend on the concentration in the end. Certainly, right. Okay.
So here you have 0.002 or 3. So, yeah.
I think everybody knows that.
Yeah.
So I think, Ulla, you can get into contact with Keld directly on some of the other questions, like me and others, and I'm happy to inform that feel free to reach out if you wish to know more about the ILC. So contact Mark Gonzalez as well at OECD, as well as those you indicated, Keld. Thanks a lot for keeping us up to date, and we are looking forward to the results of the interlaboratory comparison starting soon, and being certainly a very important contribution for not only for read across, as you did already explained at the beginning of your presentations, for the different various assessments to be made within regulatory issues. So thanks again, Keld, and I'm very happy now to
You're most welcome. Thanks.
Thank you, Keld. Sorry. And I'm very happy now to say hello to Eric. Eric is representing Go4Nano and the work done in Go4Nano towards test guidelines. So Eric, you may try to present the slides, or how is that organized?
I'll try to share. I hope you can see it now.
Perfect. So we are looking forward to your presentation, Eric.
Okay, thanks. Hello, everyone. And as Thomas already explained, I'm going to bring you up to date with the status of current work on OECD test guidelines in Gov4Nano. Briefly on Gov4Nano, which is much bigger than the work on harmonized testing guidelines, but it is an important part of that project. So just to illustrate that that's much more is going on in Gov4Nano. This is looking familiar, I guess. At least Thomas presented this earlier on today. Here I focus on the ones that Gov4Nano is involved in, and I also like to highlight that 2 of the test guidelines on physical-chemical properties were published this year. One on volume-specific surface area and one on particle size distribution. There's a lot of projects ongoing in Gov4Nano, but the ones that are also in NanoHarmony are already presented by Thomas. So I will focus here on the last few on this slide. So the aquatic environmental transformation, apparent accumulation potential, the in vitro skin sensitization, and the guidance on release tests. And for each of them, I will go through a bit of background, a bit of progress, and a bit of outlook. So starting with the abiotic transformation of nanomaterials, the transformation is a major pathway of nanomaterial transformation in the environment, the abiotic transformation, that is. So to determine transport, distribution, and assess exposure of organisms in the environment, this is an important process to have insights in. So that's why the project here aims to get the important and relevant parameters to consider in the investigation of nanomaterials transformation, develop and identify suitable experimental approaches, media compositions, analytical techniques, those type of things, and then bringing it forward to an OECD guidance document. So first a guidance document, and that will in the next step also, at least that's the aim, come up with a related test guideline for these processes. A bit on the work that is ongoing or more or less finalized, since Gov4Nano is ending early next year. The selected method to investigate transformation is to fix the nanomaterials on electronic microscopy grids, analyze them on those. The method has been tested against a realistic exposure, and there were some differences in transformation reactions observed between realistic, near-natural, and synthetic, but under similar exposure, both methods show similar results. So good to see that both the synchrotron and the TEM show similar results. And currently the results are fed into a deliverable for Gov4Nano as indicated in November, so that's nearly there. And then in a new project funded by Germany, the further work will go on a specific test guideline here. And briefly on the timelines, the project started more or less in 2020 with the definition of the pathways. Then the experimental strategy followed a year later. Comparing the synthetic media was done. And currently we have a description of methodology and results as I said, in a deliverable. And then in the coming years, the project will move onwards to a suite of TG and related guidance document for environmental transformation, aiming to be finalized by 2024. And for the other projects within Nano, I used a similar approach. So for the apparent accumulation potential for nanomaterials here, the aim is to make recommendations to to make give the possibility to test nanomaterials with test guideline 305 on fish bioaccumulation. But there are some difficulties there related to the limited solubilities and stabilities in water. So to account for those, well, in many of the cases, preferred route of exposure will be via the dietary exposure here instead of the water exposure. And another issue here is the problems to determine the nanomaterials in tissues, so distinguish them within the tissues. And we've heard already some of that before by Rob. So for this project, the objectives are to further develop bioaccumulation testing and provide further guidance. And the expected outcome is then a guidance document that provides the insights and help people do a 305 test with nanomaterials. Scientific work has been ongoing in this part, which was captured in several reports. Available information on bioaccumulation studies and analytical techniques was captured in one. The fish feed spiking was further developed and tested, which is reported in a report. The analytical techniques were examined to have a look also in the fish tissues, and some bioaccumulation assays were performed, and BCFs and BMFs, so both aqueous and dietary exposures were done for several materials as indicated here, and also those results are now available publicly in papers as well as reports. The upcoming is some further work on the analytical side for the more difficult ones. The metal nanomaterials appear to be methods appear to be good enough to tackle those, but clearly CNTs are more difficult to distinguish from tissues. So there's still some work ongoing and needed there. There's some interlaboratory comparison study on the fish feed spiking, how well that works. And then the next step is to draft the actual guidance document. And again, a brief timeline, which started on in April 2018 already, when it was brought towards OECD to develop a guidance document. And then from 2021 onwards, generation of new data and transformation and information and drafting of the guidance documents started and will continue towards the coming year and aims to be finalized by 2024. On the human health side, there's a project that was looking at the applicability of the key event-based test guideline 442D for in vitro skin sensitization testing of nanomaterials, where the focus was on the luciferase method as indicated, and that there was some experimental tests done to evaluate whether it's fit for purpose and whether some adaptations are needed. And the initial objectives focused on the recommendations for adaptation of the specific test guideline, and also validation of future adaptations of related test guidelines, which all are in the same excuse me, which are in the same ALP. So all test guidelines 442 series focus on the same ALP. So maybe there's some further work there to be done, but for now there's a background document compiled, and that is now, as indicated here, in the first commenting round at the OECD WNT, and a second commenting round is will be done, and then expected to finalize the study report in and acceptance in the next WNT meeting in April 2023, which then will lead to a publication in 2020 in the summer of 2023. Then the final topic of this presentation is on the guidance on release tests for manufactured nanomaterials. It's clear that release is a first step towards exposure, and the current project here focuses on workers, consumers, and the environment, and getting a grip on exposure assessment, life cycle assessment, safer by design approaches. All of these can benefit from release tests. And such tests provide qualitative and quantitative information about the amount and state of released materials during a specific process. But so far, there's no detailed guidance on that available. There's some guidance, but not as detailed. And now this project focuses on providing guidance on available release tests that are applicable, link these to release scenarios and processes, and then see how they can be used for things like the life cycle and the safer by sustainability approaches. This is a project that focuses on an WPMN guidance and not really into the test guideline program of OECD, but still guidance, useful guidance can be developed there as well. And the idea is to include a decision framework to help producers, processors, and users of manufactured nanomaterials to choose the appropriate release test. Here the progress is on, well, there is a compilation of release tests, and the applicability is reviewed. The draft decision framework has been developed and needs some further development, and then based on around that, detailed guidance will be written. And here, if you have any contributions that you think you can add, feel free to contact OECD on that. Then briefly again on the timeline, the project was first a proposal was first presented in the summer of 2021, and then regular meetings took place. There was some further keeping WPMN posted on the progress, and by now, well, probably early next year, the actual development of the guidance will start, and then having a first draft ready in the spring, and then a year later, final draft, and then it should be finalized by June 2024. So to summarize those timelines, the transformation is aiming for finalization by 2024, and so is the apparent accumulation potential and the release tests. And as I said, the in vitro skin sensitization should be finalized by next year. And then as a final slide, I'd like to raise your awareness on a final project conference from the projects NanoRego, RISC-ON, and Go4Nano, which all are working on risk governance of nanomaterials, and they have an online session on the 31st of January 2023. So that's upcoming January, and you're all welcome. And there's a link here if you're interested, where you can find further information. And that was my last slide. So thank you for your attention.
Thanks a lot, Eric. And certainly if somebody has some questions also to the first two presentation of this first block of this morning, those are very welcome. And Eric, you said it in the beginning, and you had a nice overview slides on activities for Go4Nano related to the activities and finalization, which are only Go4Nano. And just for all, to repeat what you said in the beginning, there are also the dustiness testing, the surface chemistry, and the solubility dissolution rate, which was started and worked on in Go4Nano. And some of the results will lead, or all of the results of Go4Nano will lead to further test guidelines and guidance documents, but then being published or coming to the OECD at a little bit later stage, and hence are more related at that point of time than to NanoHarmony, even though it was a collaboration between Go4Nano and NanoHarmony.
I'm not seeing any questions, Thomas.
Good. So there are not any questions, and we are slightly ahead of time, but I think a lunch break of 30 minutes for those who are preparing a little bit of lunch is anyhow challenging. So if there are no urgent further questions, then I'm happy to leave you all for lunch, and we will meet back at